The development of laminated glass and its use in the building industry made it possible to design transparent glass structures. These structures are commonly manufactured from laminated glass, which offers high load capacity and safety. However, the design must take into account the polymer interior that is inserted between the glass plies. The material properties of this interior influence the behavior of laminated glass, especially under loads applied perpendicular to the surface of the pane, such as floors, railings, roofs, and canopies. Laminated glass panes are subject to bending in many applications. Also, the polymer interiors have much lower stiffness than glass. They provide interaction between the individual glass plies. The important parameters for the bending performance of laminated glass are the material properties of the interior, in particular the shear modulus. This material property is time and temperature dependent. The graph shows the shear stress-strain diagrams for common PVB, extra strong PVB, and sentry glass interiors. The shear modulus is represented by initial slope of the curves. The next graph shows the behavior of the PVB interior at variable temperatures. It should be noted the slopes of the curves are different depending on the temperature. The highest slope and the highest shear modulus is observed at 0 degrees Celsius, which is shown by the blue curve. The shear modulus is decreasing for increasing temperatures represented by green, yellow, and red curves. The shear modulus is high for short-term load as the wind load, but it is lower for long-term loads. This can be observed on the graph where the stress-strain curves for 3 tests of the PVB interior with different load rates are presented. The shear modulus of the interior affects the normal stress distribution over the cross-section of the laminated glass in bending. The shear modulus is low under long-term loading or at high temperature as shown on the left picture. Plies do not interact as if they were not connected by the interior. The stress distribution in real structures, for example glass floors or roofs, is influenced by temperature and load duration. These structures are commonly exposed to temperature between 0 and 80 degrees Celsius. Partial shear coupling between the glass plies needs to be considered when the stress in glass pane is evaluated. However, when the shear modulus is high, full shear coupling of the glass plies is ensured. This is typical for short-term loading or low temperatures as shown on the right picture. The pane then acts as a monolithic in bending. Numerical study was performed on square pane made from double-layered laminated glass, which was simply supported along 4 edges and loaded by uniformly distributed load. Relation between the largest normal stress and the shear modulus of the interior is shown in the graph. The blue curve shows the normal stress on the tensile side of the upper ply, while the red curve corresponds to the normal stress on the tensile side of the lower ply. It is obvious that the full shear coupling between the glass plies occurs when the shear modulus is close to 10 megapascals. In this case, the normal stress on the tensile side of the upper pane is equal to 0. The same numerical study was used to demonstrate the effect of the interior type on the largest normal stress. The stress of the glass pane with 3 interior types was computed. It should be noted the stress in the glass pane decreased with increasing shear modulus of interior. The design of laminated glass panes with polymer interior was traditionally based on conservative practices. The favorable effect of shear coupling between the individual plies was not considered when determining the stress and deformation of the laminated glass elements. Such procedure leads to safe but non-economical design as it results in laminated glass with larger thickness. When the material properties of the interior as a function of time and temperature are known, numerical model using finite element method can be used to accurately determine the stress in the laminated glass pane. simplified analytical model based on the effective thickness method according to EN 16612 can also be used for linearly supported glass panes subject to uniform loads. Design methods for other boundary conditions or other types of loading are given in EN 19100. Simplified design procedure called effective thickness method is introduced by EN 16612 standard. Laminated glass pane is converted to monolithic glass with effective thickness. Different procedures are used for calculation of the deflection and calculation of the stress in each ply of the composition. The effective thickness for calculation of the deflection is determined according to this equation, where HK are the thicknesses of the individual glass plies and HM represent the distances of the center of gravity of the ply to the center of gravity of the whole laminated pane. The effective thickness for the calculation of the stress is determined according to another equation. The influence of the shear coupling in the formulas is introduced by shear transfer coefficient omega. This coefficient depends on the type of interlayer, load duration, and temperature range of the considered load. It takes value between 0 in case of no shear coupling and 1 for full shear coupling. The coefficient omega shall be determined according to the procedure given in EN 16613. The interlayer needs to be classified into stiffness classes according to its behavior. The typical behavior of different interlayers is shown here. The class 2 curve is characteristic for ionomer interlayer. The middle curves describe the behavior of the conventional PVB interlayers of class 1, and the lower curves are typical for acoustic PVB interlayers of class 0. The material properties of viscoelastic transparent interlayers are very important for out-of-plane loaded glass components. The composition of the laminated structure elements needs to be selected with respect to the static function, design load, and the environment, especially the temperature, which affects the shear modulus of the interlayer and consequently the resulting deflection and stress. The table compares the effective thicknesses for different types of loads for sentry glass, rigid interlayer, and common PVB interlayer. It is evident that the duration of the load has significant impact on the effective thickness and thus on the stress and deflection of the laminated glass pane.